How's it going, guys? Welcome to week 2 of our online lecture series, or week 12 of the overall semester. We have completed chapter 14, so we looked at acid-base titrations. That's going to be one of the first topics that's going to be on your upcoming exam number 3. And this week we're going to be looking at chapter 15, and we're going to complete all of chapter 15 this week. And in particular, just section 1. So you don't, if you're doing your readings at home, you only need to read section 1. We're just looking at how salts dissolve in solution. So in Chem 151, we discussed what solutions were. They were solutes, which were some type of dissolved species that was in very low concentrations that we threw into a solvent, which was commonly going to be water. And in this particular class, it's always going to be water as well, as it's the universal solvent. And a lot of salts dissolve readily in water due to water's polarity, attracting the charges on our ions, kind of pulling them out of their crystal lattice. Another thing we looked at was solubility rules. Solubility rules were ones that we either had to memorize or ones that were provided for us on an exam. And in a double replacement reaction, we called them precipitation reactions, as the driving force of the reaction was one of our products became a solid and precipitated out of solution. So what we saw was the attraction between the ions and the salt were so strong that no water molecule could pull them apart and keep them in solution. When we talked about it, we just kind of memorized or had these solubility rules provided for us, but we never discussed why these solubility rules exist. And that's the kind of goal of this chapter, is why do we have these solubility rules? Why is silver iodide insoluble while sodium iodide is soluble in solution? So solubility is a system that's in equilibrium. So we've discussed equilibrium. It's come back in our weak acid, weak base chemistry, and it's going to come back again once we start dissolving salts in solution. So we're going to have a new K value, or equilibrium constant, that we are looking at. And what we'll find is that if we make changes to external conditions, whether that be the temperature of the system or the pressure of the system, or most importantly for us in this particular topic, the concentration of a system, it can drastically shift the equilibrium in one direction or the other. So we're going to revisit Le Chatelier's principle one more time. So these changes in the condition can cause either salts to dissolve out of solution or to dissolve in solution or to precipitate out of solution. So we're going to try and use this to our benefit in a lot of cases. So a lot of industrial processes, as well as biological processes, utilize solubility to its advantage. And we're going to try and find ways that we can either drive a reaction to dissolve ions in solution, or we're going to find a way to precipitate these ions out. So here are just a couple of ways that we use solubility rules, or driving this equilibrium in a given direction, to our advantage. So the mining of seawater for magnesium. So our goal in this is to collect elemental magnesium. And one of the biggest resources for magnesium is in seawater. And it exists as a magnesium salt. So it exists as magnesium 2+. And so what we can do is we can find ways to precipitate that magnesium ion out of solution. So we can add an abundance of sodium hydroxide, let's say, to form magnesium hydroxide. Magnesium hydroxide is very insoluble and will precipitate out of the bottom as a white powder. So now we can collect that white powder, and we can then do a series of other reactions to isolate the magnesium that was in that magnesium hydroxide. And so what we did is we added that hydroxide ion to precipitate it out of solution so that we could at least have a starting material to work with. Treating hard water is something that we use these equilibria for all the time. So for treating hard water, a lot of times you guys are going to add sodium chloride or potassium chloride to a salt or to a solution. And what happens is you add a common ion, and that precipitates out magnesium ions as well as calcium ions, which are the ions that are responsible for hard water. So we're using this equilibrium to our advantage in order to precipitate out the unwanted ions, or possibly the wanted ions, in our solution. So let's look at an example of when we want to prevent something of dissolving. So an ionic compound that is known as calcium hydroxyapatite is what teeth are made out of, and that has a formula of Ca5PO43OH. So it can break down into its respective ions of calcium, phosphate, and the hydroxide ion. One of the biggest issues with keeping our teeth healthy is that when we eat diets that are heavy in sugar, bacteria will feed on those sugars and produce lactic acid. When lactic acid comes into contact with this hydroxy group, it undergoes a neutralization, and that lactic acid reacts with it and causes the tooth to decay. So basically what happens is it pulls these ions out of their solid state and into solution. So every time that we're drinking or taking in some type of liquid, it acts as a solvent and takes those broken up ions and basically pulls them out of our solid tooth. And that's what we don't want to do. So commonly we'll brush our teeth to try and remove bacteria. That way that bacteria won't produce the lactic acid, which therefore won't react with our calcium hydroxyl apatite and keep that solid structure intact. So that's an instance where we don't want a substance to dissolve. In other cases, we do want a substance to dissolve. So if we were to take an antacid tablet, we would ingest calcium carbonate. And we want that calcium carbonate, which is a solid, to dissolve into its respective ions of calcium and the carbonate. The reason why is my carbonate ion, CO3 2-, is a weak base. And that weak base can react with an excess of acid that's built up in our stomach. If it doesn't dissolve, then we don't have access to that carbonate ion, and therefore we don't have an ability to react with that excess acid. So what happens is the carbonate in its ionic form reacts with the acid to form some type of salt and water, and that water basically lowers the pH of our system. So we're able to control the equilibrium by the application of Le Chatelier's. We're increasing the concentration of a substance, or in this case, decreasing the concentration of our acid and driving the reaction in our desired direction. So let's look at how we can even start with formulating a solubility product constant. So a solubility product constant is an equilibrium constant. It basically tells us what the ratio of products to reactants are in a particular salt dissolving in water. So here let's take one called silver chloride. Silver chloride is not very soluble, so it tends to precipitate out of solutions relatively easily. If we were to add a large excess of water, it would dissolve only to a small extent my silver ion and my chloride ion. So we're taking that crystal lattice and we're breaking it into its respective ions. Every time that we are solving for a solubility product constant, the very first thing you want to do is write an ionic equation. And we have our ionic equation for silver chloride listed below. So this is the type of equation that you should be writing for every single problem that we focus on in this chapter. You're going to start with the solid that we have, so the salt that's been provided for us. So silver chloride, and then in parentheses S, indicating it's a solid. So our solid is always going to be our reactant. Then we'll have those double-ended arrows signifying that we are in equilibrium. And only a small percentage of this silver chloride will dissolve, and when it does, water molecules are going to pull those ions apart and form my silver plus cation, aqueous, plus my chloride negative ion, aqueous. So that's what our general ionic formula is going to look like. We'll start with our solid, and then we'll have our equilibrium sign, and then we'll break into its respective ions. So the solubility product constant is a dynamic equilibrium. So what that means is some solids are dissolving, and at this very same time, silver and chloride ions recombine to form the solid. So we've reached a state of equilibrium where the rate of our forward reaction, the dissolving of my solid, is equal to the rate of my reverse reaction, where the ions are reforming to form my solid. So that there's always a constant concentration of my solid precipitated out of solution and my ions dissolved in solution. So let's write our solubility product constant, or our equilibrium constant, for dissolving a salt. So when we are writing this equilibrium constant for a slightly soluble solid and a solution of its ions, we're really only going to focus on the products. The reason why is because when I write my K expression, it is always the concentration of the products raised to their respective coefficient divided by the concentration of the reactants raised to their respective coefficient. But in the case of these dissolving salts, my reactant is always, always, always a solid. And since we ignore solid concentrations in my expression, we are only going to focus on the products in these particular K expressions or equilibrium constant expressions. So in this case, my KSP, that SP stands for solubility product, it just means the equilibrium constant of dissolving a salt in solution, is equal to the concentration of my silver ion times the concentration of my chloride ion. What we see is both of them are raised to the power of 1 only because the coefficient in front of both of them is 1. If I had a coefficient of 2 or 3 or 4, we would raise it to that respective power, just like we've done throughout all of our equilibrium studies. So when asked to solve for the solubility product constant, our solubility product constant is equal to the concentration of the products raised to their respective coefficients. And then we're not going to divide it by the concentration of the reactants simply because our reactants are always, always going to be solid. So lastly, let's take a look at solubility product constants. So these are all provided for you in your textbook. Your textbook, you're going to be looking in your appendix. And your appendix is going to give you an opportunity to see what is the KSP for each of these salts. So if you're not provided with a KSP, it's assuming that you have access to your appendix and that you can find these values in the back of the book. In your exams, they are obviously going to be provided for you in the question. You do not need a list of these KSPs. But they are located in Appendix J of your textbook. And what we see here is these are my KSPs at 25 degrees Celsius. Remember, any of these equilibrium constants are temperature dependent. We're always going to focus on these KSPs at 25 degrees Celsius. So anytime you see a temperature in your problem, you can ignore it. There's nowhere in the problem that you're going to have to actually plug that value in. It's just saying at this specific temperature, this is its KSP. Let's compare a couple of these guys. Let's compare my copper 1 chloride and my aluminum hydroxide. So my aluminum hydroxide has a KSP of 2 times 10 to the negative 32. And my copper 1 chloride has a KSP of 1.2 times 10 to the negative 6. If we are looking at the concentration of my products over reactants, the larger the KSP value, so in that case, or in this case, it would be that copper 1 chloride, the more likely that salt is to dissolve in solution. So copper 1 chloride will dissolve in solution more so than aluminum hydroxide. So when we're comparing two different salts and trying to identify which one will dissolve versus another, we're going to identify which one has the larger KSP. The larger KSP indicates the more likely that salt is to dissolve in solution. So here we have them in decreasing order of solubility. So as that KSP gets lower and lower and lower, less and less of that salt is going to dissolve. So the next lecture series that we're going to start putting together some of these formulas and solving for molar solubility as well as KSP values.